Hi, this is Thomas George. I'm going to walk you through our recent TMLR paper on model probing methods for detecting mislabeled examples, which is joint work with Pierre Naudet, Alexis Bondu, and Vincent Lemaire at Orange Innovation. So why are we interested in mislabeled examples? When you train a machine learning model, it learns from your training data. So ideally, you would want to get as many training examples as possible, but also the quality of the training data is paramount. In particular, it should be free from labeling errors. In real life, there are many reasons for getting mislabeled instances, such as some examples might be ambiguous or subjective, your annotators might make errors, or if you want to automatically annotate your training instances, you might be interested in designing automatic labeling rules, which are often imperfect, or you might obtain your labels from an imperfect sensor or from a database that you don't 100% trust. Our motivation for automatic methods for detecting mislabeled training instances is thus to improve the quality of our training data while reducing the need for manual labeling. How can we automatically detect these mislabeled instances? Here is an example strategy. First, train your favorite classifier on the training data, then predict the class on the exact same training instances. If the predicted class is different than the label given during the annotation process, then flag this example as being potentially mislabeled. What we did here is that we train a classifier on some data, then we used this train classifier to diagnose our training data. Why would that work? The rationale is that there is some form of robustness to noisy labels embedded in classifiers, which makes them treat genuine and mislabeled examples somehow differently. Here, we simply queried the trained model for its predicted class, but as we will see next, there are many other ways of inspecting trained models. Our observation, while surveying existing methods, is that many of these methods follow a very similar pattern. This simple strategy gives a binary answer. Either it considers the example as being trusted if the predicted class and the observed class match, or untrusted otherwise. We assign to each example a scalar trust score that is either 0 or 1. But in general, these trust scores can take any real values. How do we compute these trust scores? Most methods can be viewed as belonging to the family of model probing methods using a simple framework that I am now going to describe. First, we need to specify a family of machine learning models, and it could be any classifier, such as XGBoost, a deep neural net, a linear model, and so on. This is our base model from which we will get a signal used to discriminate between genuine and mislabeled instances. How do we get this signal? We measure some characteristics of this base model applied to every training instances. We call this to probe the base model. In the simple example of last slide, we use the predicted class that we compared to the observed class as our probe. But in more generality, there are many ways of probing the base model, such as using the loss, the confidence, or the margin of the observed label. There are also more intricate probes that compute some proxy of the complexity required to learn every example, such as the prediction depth in deep nets. Another way to probe is by using influence functions and siblings such as tracing, and so on. The third component of this framework is that rather than using a single base model, we could instead use an ensemble strategy such as bootstrapping and train a set of different base models that will each provide a slightly different version of the probe scores. Here, each base model is trained on independently drawn subsamples of the training sets. They can be considered to be on equal terms. But in contrast, progressive ensembles, such as boosted ensembles, are iteratively built, and there is a natural ranking between weak learners. Early iterations learn prominent patterns, which ideally would correspond to clean examples, whereas late iterations learn more intricate areas of the feature space, rare examples, as well as mislabeled examples. And the two main members of this family of progressive ensembles are boosting methods as well as deep networks, which are also trained iteratively and which can be probed at several checkpoints during training. Because of this analogy between boosting and deep learning, methods designed to work with deep networks can be readily adapted to boosted models. We explore this idea further in our experiments. Using an independent or progressive ensemble strategy produces a number of probed scores for each training instances. So the fourth and last component of the framework is how to aggregate these sets of scores into a single trust score for each training instance. And depending on the probe and ensemble strategy, it might make sense to use the mean score or majority votes, or instead to use some form of difference between trust scores, such as in the bag out of bag difference, or variance of trust scores. With these four components in mind, we are now able to categorize a large number of existing methods found in the literature. So here we have a table with the four columns corresponding to the four components of the framework: base model, probe, ensemble strategy, aggregation method. The last column contains references to papers that proposed the methods. And as an example, in the area under the margin method, or AUM, the base model is a deep net that we probe using the margin. The margin is computed at every iteration during training, and these margins are aggregated by simply summing iterations. With this framework, we can perform a systematic comparison between methods by looking at which components are the same or which are different. Or we can also design new methods by exploring new combinations. This framework is not just an abstract view on existing methods. It can also be actually implemented, and we also provide a library that does exactly that. So in the area under the margin example, it goes as follows. Specify our base model as being a multi-layer perceptron. Probe using the soft margin probe. Use the progressive ensemble strategy that will compute the margin at every iteration. Then aggregate these margins using the sum. With this detector, I can now compute trust scores for my training examples. Now, if I want to experiment with AUM but on gradient boosted trees rather than deep networks, I can just replace the base model with a GBM classifier from scikit-learn, and the library will do the rest. So here, rather than probing at every iteration of the deep network, we probe at every boosting iteration of the boosted trees. The library is available on GitHub. It follows scikit-learn's syntax so that every machine learning practitioner should already feel at home. It comes with a series of predefined detectors from the literature, and you can design new detectors by combining existing components or by designing your own way to probe machine learning models. Equipped with this library, we then perform a series of experiments in order to benchmark the detectors in the very same experimental setup. And the first metrics that comes to mind in order to evaluate a detector is how good it is at detecting mislabeled instances. So provided that you have ground truth labels, this could, for instance, be measured using the area under the ROC curve. But not all examples are equally important. Some examples might be more valuable than others, for instance, because they reflect a minority pattern from the training data. So we instead benchmark the detectors using fully automated pipelines. In the first one, we compute the trust scores using a detector. Then we filter our training datasets in order to discard less trusted examples. Then we train a classifier on the filtered datasets. Finally, we compute its test loss. Similarly, in our second pipeline, we compute the trust scores, then we relabel the 10% less trusted examples using ground truth labels. We train a classifier on these new datasets, and we compute its test loss. In both cases, the test loss reflects how good the detector is at detecting mislabeled examples that are useful to train a final classifier. In our benchmark, we use a series of tabular and textual tasks with varying size, noise level, or class distribution. And the labels come from a set of automatic labeling rules, which gives non-uniform labeling errors, also known as noise not at random. This is a more realistic but also more complicated type of noise than uniform noise. Using this benchmark, we conduct a series of experiments on the role of the validation sets, the benchmarking of different detectors on the same tasks, some strategies for filtering trusted and untrusted examples, and so on. For further details and insights, please read our paper on Open Review or contact us if you have any questions. And thanks for your attention.